There are four mechanisms how this works, and the first mechanism we're going to look at is conduction. Now, conduction only works in solids. There are two mechanisms by which conduction works. You have the vibration of the ions in the lattice. That's the arrangement of the particles in your solid that we looked at when we looked at solids, liquids and gases. Now that is all solids. Whether they are conductors or insulators, all solids do that. But it's very slow. And you have the movement of free electrons. Now, of course, only conductors have free electrons. And that's mostly, almost entirely metals. Graphite's in there too. Graphite's a special case. It's also got free electrons. It is a thermal and an electrical conductor, but mostly the materials with free electrons are metals. So how do we explain conduction? Well, we supply thermal energy to one end of our solid, whether it's a bar or a block or whatever. The kinetic energy of the ions at this end increases. They vibrate faster. Now note, they vibrate, keyword faster. They were vibrating before. This comparative is essential. They don't start to vibrate, they were vibrating, now they're vibrating faster. It's only at absolute zero, minus 273.16 degrees centigrade, that these vibrations stop. So in every circumstance you'll ever come across, the ions in your solid are vibrating. Note the use of ions, another key term. It isn't atoms, it isn't molecules, it is the ions in your solid. I should have said up here, this is your molecules. I was thinking metals. It's ions in metals. So, talking about metals, this is what happens. They vibrate faster, passing the Ke from ion to ion. This, of course, is slow. The main mechanism in metals and conductors is that the free electrons gain kinetic energy. They then move down the solid because they can. Collide with ions, pass on kinetic energy. So they vibrate faster. So if we're talking about an insulator, we would have the word, we'd have the word atom or molecule in here and here. This is our main mechanism. Oops. This is our main mechanism in metals. And in metals, it is crucial we talk about ions vibrating faster. That gain of kinetic energy there, right? So that's conduction. All solids, you have the vibration of the molecules or the ions in the case of a metal in the lattice, but that's slow. In conductors, you have the movement of free electrons, and that's almost exclusively metals. The process, you supply thermal energy to one end of your solid. The Ke of the molecules in any substance, the ions in your conductor at that end increases. They vibrate faster, passing on the Ke from molecule to molecule in non-metals, apart from graphite, ion to ion in metals. The main mechanism in conductors, that is to say the one that allows conductors to move thermal energy quickly, is that movement of free electrons. So when you supply your thermal energy to one end, the free electrons at that end gain kinetic energy. They move down the solid and collide with ions in the solid further down. That means they pass on kinetic energy. That makes those ions vibrate faster. Two mechanisms for conduction. Convection then. Well, that's liquids and gases. Now, this is one that's not focused on in the syllabus particularly, but I think in terms of context, seeing why conduction doesn't work in liquids. Why do we have to have a separate mechanism? Well, remember, conduction relied, if I go back to conduction, conduction relied on two things. The vibration between the ions. So you had, let me just stick another sheet in here. You had your molecules or your ions bonded together, touching. And what you're doing is you're making this one vibrate faster, which makes this one vibrate faster. Now, the vibration is passed along through the bond between the two, but in a liquid there is no bond. And so, let's say, for example, the vibration of this one is in this direction. Well, in a liquid, that vibration is not going to get passed on to this because they're not actually bonded together. They're not connected. So, if I take my liquid and I supply thermal energy here, then the surface of the liquid gets warm, but those vibrations can't get passed down through the body of the liquid because there is no mechanism to do that. The other thing about liquids, which you may know from chemistry, is that liquids generally are covalent, which means there are no free electrons. how liquid molecules form. They are covalent bonds, and so there are no free electrons. And so the other mechanism for conduction, free electrons, can't happen. And because the atom's molecules are not bonded together, molecule to molecule, I mean, then the transfer along that bond can't happen either because it's not there. So conduction doesn't happen in liquids very well. In fact, water is a very good insulator. If you've ever gone swimming in the sea, somewhere hot, Mediterranean or whatever, you'll have noticed that there is a layer of water on the surface that is warm, but as soon as you go below that, it's really quite cold, and there's a distinct temperature change across this boundary. So this is why we need this other mechanism to transfer through liquids and gases. So convection, then, you take your liquid or your gas, but I'll take a liquid to start with. If you supply some thermal energy here, what will happen? Your molecules gain kinetic energy, and now they are moving, not vibrating, they're moving faster. So the warmer liquid or gas I'm just going to get rid of that. Expands, keyword, because the molecules take up more space. So the density falls, that is to say the density of that liquid or gas that has been heated falls, not the density of the molecules. It is not the molecules that expand, it is the liquid or gas made up of the molecules. Literally, the molecules are moving around faster and taking up more space. So the density falls. Remember, that density is the mass over the volume. The mass hasn't changed, but the volume's got bigger, so the density has fallen. And so the warm liquid or gas rises. Of course, then it will mix with cooler and fall, the reverse process, and five, we have cooler liquid or gas, pulled in to take the place of the heated stuff in step one. So that's convection. That happens in liquids and gases. Obviously, because it involves the actual movement of the molecules, it can't work in a solid because they're bonded together in a solid and they can't move around, they can only vibrate. So convection doesn't work in solids, and conduction doesn't work in liquids because conduction relies on passing the vibration bond along the bonds between the atoms, molecules, ions, and on free electrons primarily. Good conductors have free electrons, but liquids don't have free electrons because they are covalently bonded. So convection doesn't work in solids, conduction doesn't work in liquids and gases for those reasons. Then we have radiation. Radiation, in this particular case, we are talking about infrared radiation exclusively. This is thermal energy transfer. There are other kinds of radiation. You've got ionizing radiation. You've got all the rest of the electromagnetic spectrum, including a couple of ionizing radiations as well. But here we're talking about thermal energy, we're talking about infrared radiation, and radiation, as we know, does not require a medium to travel. So this is how the sun's energy gets to us from the sun to us through space. It couldn't work by conduction or convection because there is no medium. There's a vacuum between us and the sun. So a few things about radiation. The factors that affect the loss of heat by radiation. You have surface area. So if you want something to cool more quickly, increase the surface area over which that cooling takes place. The temperature difference. Between the object and the environment. The thing is, your object is absorbing radiation, infrared, from the environment. You sit in the room and the room is supplying you with infrared, but you are also emitting infrared. Now, if you take an inanimate object, because we're more complex, take a cup of tea, for example, the cup of tea is generally warmer than its environment, and so it's emitting more than it's receiving. But there comes a point when the tea and the environment it's in are at the same temperature, and so the emission from the tea and the absorption by the tea of infrared is happening at the same rate, and so the tea remains at a constant temperature. But the bigger that difference, the bigger the difference between what is being emitted and what is being absorbed. So your tea will cool fastest when it's hottest on a cold day. So if you take a cup of tea and you make it in August, hopefully August is nice and hot, it will cool down more slowly than it will in January, assuming that the room is colder in January. But as it cools, the rate at which it loses the thermal energy falls. So you'd have a cooling curve that looks a bit like that. So as the temperature difference falls over time, the rate of cooling falls. So the colour and texture of the surface. So Dull black surfaces are good at absorbing and emitting. So if you want something to cool down quickly, like for example the heatsink in a computer, like for example the radiator in a car, like for example a wood burner that you might have in your living room, paint it dull black. If you want something to absorb lots of thermal energy, then paint it dull black. Solar panels, for example. If you are using solar panels to heat water, then the pipes through which the water runs will be painted matte black or dull black, so that they absorb the infrared from the sun. Shiny silver is the contrast to that then, mirrored. These are good at reflecting. These of course are poor at reflecting. And since this reflects, it is a rubbish absorber, because if you're reflecting it, you can't be absorbing it, and it's a poor emitter. So if you want something that is hot to stay hot, make it shiny silver, the outside of a saucepan, for example. If you want something to stay cool, then paint it or colour it shiny silver. So this is going to reflect radiation, so you might make the inside of your saucepan, shiny silver as well. So it reflects. They don't tend to, but you could do, so that radiation is reflected back in. So that's the factors that affect radiation: the surface area, the temperature, the colour, and why these colours are good at what they are and poor at what they are. Clearly, if you are absorbing, you're not reflecting. If you're reflecting, you're not absorbing. So that's radiation. There is another mechanism which is really interesting, which is evaporation. Now, this is one of the main mechanisms by which your tea will cool down. Taking you back to what we said before about temperature being a measure of the average kinetic energy. Let's take the example of a cup of tea or something like that. So you have an average kinetic energy in here, which is reflected by a temperature of, let's say, 95 degrees centigrade. Now, within that, of course, because it's only an average, some will have more kinetic energy, some will have less. So up here, the ones with the most kinetic energy, the ones moving around fastest, and therefore the least dense liquid or gas, but in this case it's a liquid because we're talking about evaporation. This is where the most energetic ones are. And what you would see, if you could look closely enough, you would see some of these molecules leaving the surface and falling back. But some of them will leave the surface and not come back. These are the most energetic ones, the ones that have enough energy to leave the surface and not come back. As a consequence, because they are the ones with the most kinetic energy, the average kinetic energy in here will fall, and so the temperature falls. So Clearly you've got your radiation from the sides as well, but you've got this loss of the most energetic molecules, which is causing the temperature to fall. So why are these ones not able to leave in the first place? Well, because you have atmospheric pressure pushing down. And so these molecules that are trying to leave or are leaving are trying to do work against atmospheric pressure. It's only if they have enough energy to do that that they can actually leave. So if you were to reduce atmospheric pressure, let's say, for example, you were to take your liquid in a flask and carry it up to the top of a mountain where atmospheric pressure is less, the water at the top of the mountain will boil at a lower temperature than the water at the bottom of the mountain because there's less atmospheric pressure pushing down on it to stop those molecules leaving. So they will leave when they get to a lower kinetic energy, that is to say, they'll leave at a lower temperature. So water at the top of a mountain will boil at a lower temperature than water at the bottom of the mountain because of the reduction in atmospheric pressure through climbing the mountain. So there you have conduction solids, two mechanisms. The vibration of the atoms in a non-metal, the vibration of the ions in a metal, supply thermal energy, increase the kinetic energy of the atoms, molecules, ions, and that gets passed down along the bonds. That's slow. You have in metals and graphite free electrons as well. They gain kinetic energy. They then move along and bump into the ions now because there are free electrons, there are ions, not molecules. The ions then get bumped into by the free electrons, gain kinetic energy, vibrate faster. That's a fast mechanism. Liquids and gases, you have the heating of the liquid or the gas. So they gain kinetic energy, move around faster. The liquid or gas becomes less dense and rises. It mixes with the cooler stuff and falls. And while all that's going on, cooler liquid or gas is pulled in to take the place of what rose due to a fall in density. So that's convection. Radiation then. You have this transfer by infrared, no medium required. The factors that affect the surface area of the thing, the temperature difference between it and the environment, the colour and texture of the surface, dull black, shiny silver being the extremes, and some context in which you would use these properties. And then evaporation. So that is thermal energy transfer.